Hello everyone, hope you're all healthy and are doing good. This is Gyanendra and we are back with another session in the series of your IIT JEE Preparation. So we are in this JEE Achievers batch and we have been covering up certain topics already. We have talked about things like the general organic chemistry, and now we know how and what are the topics that you already have, right? When you already have understood about the basics, like how do you approach a reaction, or what are the electron shifting effects that could be used in order to make the reaction happen, right? So those things we have already seen. We'll be continuing from that and moving forward with that. In the last class, we had also talked about different type of reaction mechanisms that you would usually use in a topic of alkyl halides chapter particularly, right? So in alkyl halides, hello Himanshu, welcome. So we had already seen many things or many topics like this, that how a reaction happens, what is nucleophilic substitution reaction, how the progress of a reaction happens, right? So those we have already covered. We'll be continuing from that. Now we'll observe and use those reaction mechanisms and look at some more mechanisms. We already have covered the substitution mechanisms. We haven't covered up the elimination mechanism yet. So we'll be covering up that elimination mechanism part as well. And we'll be moving forward from that topic onwards. All right, then without any further delay, let us directly dwell into the topic. And the topic for today is the reaction of alkyl halides. Right, you could clearly see, that molecule that is coming up, hopping on and throwing out something, right? That yellow ball is moving out of that molecule. The way that reaction is happening is that is substitution. That green ball is substituting the yellow ball. That is what happens in a substitution reaction. I hope you guys are already aware of it, right? So let us start without any delay. Yeah. And I hope your preparation for IIT JEE and your school exams are also going well, and you're doing well in your school exams too. So about me, I am Gyanendra and I have been in teaching industries for around 7 years. I've taught in FITG, Narayana, VMC, IIT and many other places. So I know about things. Alright then, without any delay, let us directly dwell into the topic. And the topic, as I was already telling you, is about the chemical behavior, the reactions of alkyl halides. You could already remember that alkyl halides would have partial negative and partial positive charge distribution. If you look closely, halogen here is an electronegative element. What would it do? It is an electronegative element. It has a tendency to attract the electron pair towards itself. Since it attracts the electron pair towards itself, the other atom with which it is attached, what would happen to that atom? That atom would be devoid of electron, would be lacking the electrons, right? And because that atom would be lacking the electron, it wouldn't have any electron with it. And for that reason, that atom would become vacant or empty of the electrons, right? And now because it doesn't have anything or any electron in it, what would it seek? It would seek the electron density. It becomes partially positive. Why partially? Why not completely? Because the electrons are just shared. Even though it is more attracted towards the halogen atom, it is still shared. So it still holds a little bit of this electron density with it, right? So that is why this molecule or this bond is going to be a polar bond with carbon having a partial positive character. The reactivity of haloalkanes would all be dependent on this type of bonding. So because it is polar, you'd see a negative group, maybe a nucleophile, attacking this molecule. Okay, and there would be situations where a base could attack a carbon next to this carrying a hydrogen atom. So you would majorly see two types of reaction here. One is the action of a base, the other would be the action of a nucleophile. Okay, so these two reactions are very common, and few more reactions were going to be that is going to be based on free radical mechanism. You guys remember, I've already talked about what is free radical and how does the free radical stabilization affect the process of a reaction. So we have seen all those things already. We'll just be covering up or moving further from that. So without any delay, let us directly move into it. Yeah, now one more important thing to be observant about, or to observe carefully about, is like if carbon is attached with fluorine and if it is attached with iodine, Like which one is going to be more reactive and why? Just imagine. Now, if carbon is attached with iodine and if the same carbon is attached with fluorine. Now, you guys might already know the carbon atom is a small atom. It has just this 2p and 2 as orbit. So, if it is attached with fluorine, which also has 2p orbital, which is going to be bonded to the carbon atom, the bonding is going to be very strong since they're of similar size. You just imagine a friend who is of your same age would be of greater bonding to you than a guy who's very old who has just met you randomly, right? So understand this: the friendship with which if with a friend who's of your age is going to be more stronger than the friendship with a person of a different age, right? And because of this reason, this bond, because it is much bigger than fluorine, breaking them becomes easy. How does it become easy? Because it is going to be pretty far from the nucleus of this, or the nucleus of the iodine is going to be pretty far from the nucleus of carbon. So the bonding isn't going to be that good as of how good the bonding is in case of Ca. And because of that, this bond can be cleaved very easily comparatively. And for that reason, can be broken easily. And because it can be broken easily, it could be very ready to react. And for that reason, if you talk about the polar behavior or the reactivity that belongs or that depends on the polarity of alkyl halide, it would be particularly alkyl iodide that shows the reactions the fastest. Okay, so that is one thing that you would need to understand and remember while thinking about it. Now, one more thing is about the type of halide you have. If you have a carbocation, when formation, tertiary ones are going to be reacting much faster than the secondary or the primary ones, right? So depending upon the mechanisms also, the reactions would get affected. One might be happening faster, the other might be happening at a slower rate. So this is about the things that you would need to understand before dwelling into the topic. Let us move and understand a few more things here. The types of reactions. Now that we are talking about the types of reactions, we should understand that majorly three types of reactions are going to be talked about in this chapter. The first one here is a reaction with metals. You guys might not know that the metallic reactions or compounds of carbon with metal is really important. There is something called as Grignard reagent. Many of you would have heard. This guy Grignard have even got the Nobel. I mean, his name was so famous that, I mean, the reason why his name was so famous is because the compound that he has made, RMGX, that is just one compound where organic substance, R represents carbon containing substance. For example, CH3MgCl. It is a compound that we call as Grignard reagent. Now this compound is such a useful compound that it could prepare a lot of things very easily. Okay, so Grignard reagent is one of the very useful organometallic compound. It has an organic group attached to it along with a metal and a halogen. Now this molecule is very reactive. The reason being, magnesium is electropositive in nature. That means it would push the electron density away from itself. Where would it push the electron density to? To the atoms that are directly connected with it, that is the carbon atom. So it would push the electron density to the carbon atom, resulting in R- formation. Now, this R- particularly is very reactive. It doesn't want to be in that state. So what it does is it has two types of nature. I mean, it could act as a base. The easiest way or the easiest action that it could show is like that of a base. It could give the electron pair to a proton and act as a base. There is one more action, like if the molecule with which it is reacting, it could like act on a substrate as a base. But let's say the substrate doesn't have a proton. Okay, if the substrate doesn't have a proton, then how would it act? I mean, in that condition, you just check for a partial positive carbon or any species that has positive character. So this R- in the absence of a proton or an acidic hydrogen can even act as a nucleophile. So that point is to be really noted well. That R- has two types of action that it could show. One, which is very easily shown or observed, is the action as a base. It could abstract proton even from water. Any source that is having an hydrogen atom, the hydrogen atom attached to electronegative atoms like nitrogen, fluorine, oxygen, even chlorine, sulfur or something as well, could be taken out by this base. So just imagine how reactive base is it going to be, right? The other action, as of what I've told you already, is its nucleophilic behavior. It does act as a nucleophile, but there is a condition here. The condition here is in the absence of a proton or an acidic hydrogen. So in the absence of an acidic hydrogen, and if you have a center which can accept electron pair, this molecule can act as a nucleophile as well. Okay, but remember, if you have a protic, let us say an acidic hydrogen, then it would always act as a base. That acidic hydrogen is even present in water. Just giving an example. So in the absence of a base, in the absence of a proton or an acidic hydrogen, how does it behave like? You could just let me know your answers in the chat box, right? Acidic hydrogen. So in the absence of a proton or an acidic hydrogen, the behavior of an organometallic compound, especially the Grignard reagent, is going to be like that of a base of that of a nucleophile. Otherwise, how does it behave? Like that of a base, right? So that's very clear. That should be very clearly known to you that the general behavior of RMGX, that is Grignard reagent, is that of a base. What a base does? Abstracts proton. Sorry. With that known, let us move. The other type of reaction is already what we have talked about. Nucleophilic substitution reaction. We have seen how nucleophilic substitution reaction works. We have talked about SN1, SN2, SNNGP, and SNI. We have observed how are they all different and what is the major difference between all of them. The major difference comes in their regioselectivity and the speed as well, right? We had observed that SNNGP happens really fast, 1000 times faster than the other processes. And then we'll learn about the last type of mechanisms and the reactions, and that's really important. And at high temperatures, this type of reaction gets preferred. Which type? The last one, the elimination reactions. Now we'll understand about these elimination reactions as well properly, and we'll look into it. So this is going to be the topic for the day. So without any delay, let us directly move into it and start the first ones. The reactions with metals. Now you all know there are certain metals which are very reactive, guys, and particularly metals like sodium, potassium, lithium, majorly sodium and potassium is what we use. They have capability to give an electron, just one electron. Now you could just understand, there is a saying, right, in Hindi, the same way, a single electron can bring calamity in the compounds like this. How? Let us observe that. So the sodium is a free radical initiator. Even sunlight or substances like peroxides, they are free radical indicators, children. So in the presence of this, there is this free radical behavior that gets generated. These are all called as free radical initiators. Could you tell me the reason why would they be called as free radical initiator? Because they simply initiate the formation of free radical. And for that reason, they convert or they create a free radical. Now you could just observe Na form Na plus, there's one electron. This one electron is enough to cause free radical development in this Rx. And since two of such groups are going to be there and two Na would come up together, form NaX, you would actually have this RR created. But then how does it work out? How does it all happen? We'd need to understand that as well, right? So we'll see what is the process, what is the cause, what makes it happen that way. We'll observe that and see and learn that too. It is simply a free radical mechanism. Many of you would have already seen what is a free radical mechanism. It's simply a three-step process. First one, it's simply the chain initiation step, wherever the free radical initiates the thing. And the second one, guys, is the chain propagation step, where it propagates the chain. And then the third one is the chain termination. So we'll see how does it work out and understand about the process. In the beginning, in the presence of an initiator, a single electron transfer, SET, happens, and that causes this double bond, this bond to get broken from here. Once the bond gets broken, you just see the transfer of single electrons with the single barbed arrows. You could understand it results in the formation of this R radical. And once this R radical gets generated, radicals are unstable. So what would it do? It would try to become stabilized. How can it be stabilized? By the presence of another species that bears the same nature, right? But then before that, like if you'd observe this one particularly, is the chain initiation step. As I told you, any free radical mechanism follows 3 steps. The first one, chain initiation step. Okay, so here the chain would get initiated. And then what was going to happen? It would propagate the behavior. It would make another molecule get the same nature. It's like this, that if the teacher started scolding you in the class, when like, why were you talking? What is the first thing that anybody would say? Ma'am or sir, this guy started talking first, and because of that I have started to talk, right? Depends. But everybody would come up with this idea. The same way, this molecule, which is this R radical, can have this behavior, that this R radical would see that there is another sodium. It would take out the other electron from that as well, and now it would form R minus ion. It would take up the other electron. And this negative ion is very reactive. R radical was also reactive, but this one is reactive towards Rx. Now what would it do is it would give the electron pair to R, causing this X to break away. Now how does it happen? This R group over here has a partial positive character. This one, because it is electronegative, is the major reason which has given the R group a partial positive character. So what has it caused? It has caused the bond to become polar, and that gave the chance to this R minus to give its electron to that R. And also observe one thing. There is no acidic hydrogen. I hope you guys know what is acidic hydrogen. Hydrogen attached to electronegative element. And for that reason, this bond would easily make an attack over here. And once the R group makes the attack, the product formation happens, and this R gets attached to R. Okay, so this is how the things could happen. Okay, we have included ionic mechanism for better understanding, but remember that it could even follow the free radical mechanism. So that is the catch that you would need to understand, that happens here. All right, so this is the point. But understand one thing: can you form any type of free radical, any type of alkane using this, or you would just get specific type of alkane using this? That is another important thing. If you try to react it with an alkyl halide of different type, there will be multiple products formed, and separating them would become very difficult. That's why Wood's reaction is good to prepare alkyl groups which are symmetrical, which has same number of carbons. But it is then good for preparation of those alkyl halides which has different number of carbons. If you try to react CH3Cl with CH3CH2Cl, you end up getting 3 products. One from self-Wood's reaction, other from cross-Wood's reaction, another from the self-Wood's reaction of the other molecule. I'll tell you what I mean. So let's say if you have CH3Cl reacting with CH3CH2Cl, and you'd say that you wanted to undergo the same reaction as what we have seen. So what we would expect it to give you is simply this thing, that is CH3 and then the other 2 groups, CH2 and CH3, right? So these 2 things should just get attached, is what our goal would be. But do you really think that it would only give you this one, or it wouldn't give you or something else? Well, that is what our expectation would be. But in reality, that is not the only thing that this molecule could give us. It would also give you a a product which is formed just by combination of 2 CH3Cl. That is this. Apart from that, there would be one more product that would be formed because the combination of the same molecules 2 times, which I'm just now circling. and that would end up giving you this. So total of 3 different molecules would get generated. Now the problem is separating them. They all would have nearly same boiling, melting and other temperatures, nearly same, not exactly same. So separating them becomes a very tedious job, and for that reason we don't use the Woods reaction for preparation of this on a scale that could be scaled up. So that is the point here, and remember that any free radical mechanism without the ionic mechanism being involved follows 3 steps. First step, chain initiation. Second step, chain propagation. Third step, chain termination. So I'll just add on that over here so that you get an extra idea for that as well. Okay. I hope you have an idea that is even there in the NCERT book. I'll just have given you a trick here for better understanding and faster approach towards the problem. All right. So do let me know if you have a doubt in the mechanism given in the textbook about the free radical mechanism. Okay. So we'll move further to the next reaction with the metals, and this reaction is something that generates the free radical, right? So how does it happen that we generate the free radical? What makes it get generated? It is very simple. We'll observe that how does it happen. I was just talking about this thing called the Grignard reagent in the beginning, if you remember. It's all about that now. We are now looking at how does the Grignard reagent get generated. Okay, and that has happened, or that would happen by the reaction of alkyl halide with magnesium. Now how does magnesium cause this? You might know magnesium is like at the top positions of the elements in the periodic table, right? In the second period, it is the second position. So it has somewhat it is a metal, but it does have some covalent character too. There is nothing which is completely covalent and completely ionic. Every ionic substance does have covalent character. Every covalent substance has ionic character in it. So both the characters are going to be present in a compound. Okay. So this magnesium, particularly because of its size and electronegativity or electropositivity, you say, and the positioning or behavior it would show, is going to be unique. It could also make up some what we call covalent character, okay, or covalent like bond. So when CH3CH2X molecule comes closer to the magnesium, it forms something like this, CH3CH2MgX. Now why does it happen? I'll tell you that as well. If you observe closely here, in the presence of magnesium, which is a metal, a free radical gets generated initially. So with magnesium's electron being transferred, this X would form a radical. Now because this X radical gets generated, over here, it has taken up an electron, right? So that would get a negative charge as well. It's a unique type of radical. And since it has been broken down, it has given away one of its electron after giving up the charge. The electron, obviously it is going to gain the positive nature, since the protons are going to be larger in number. Now, when these two things comes closer to each other, this causes this bond to get broken down, causing this molecule with one electron to get the 2 electrons and get a complete negative charge, forming an R radical. So this R radical gets joined together with this Mg radical, forming R Mg and the positive charge over Mg. Now, obviously, a positive charge over Mg is good. But charges, or a molecule with charge, is never as good as a molecule without charge. That Rmg plus would want something to stabilize them, and we have already generated X minus. Because X minus approaches it, gives its electron, forms a bond like this. And that's how an organic compound with a metal gets generated. That's what is called as the Grignard reagent. And it is very, very useful substance, as I've already told you. Okay, so we'll see how is it going to help us in various processes, various reactions, and what is the difficult, unique things that it does that makes it so useful. We'll observe that as well. The unique thing that it does is it forms R minus. Okay, and that is very reactive, children. For that reason only, it is going to be so useful. We'll see how. Now the reactions we'll see how with the process or with the flow of time. Like we'll see how it does react with carboxylic acid, aldehydes, ketone. Those all have a carbon which has partial positive character. We'll also see how it reacts with water, alcohol. It takes up the proton from water, alcohol, and all. It doesn't allow anybody which has a proton to stay as it is. It takes up the proton from that. And if it doesn't have a proton and has a partial positive center, it gives the electron density to them. So it is a very useful thing, the Grignard Reagent. The next reaction is a reaction with zinc. This is also there in your NCERT. But it's still important and people miss this type of reaction. They think that this is just a normal reaction, let us just skip it. That's how we do with inorganic substitutions or reactions. Now, if you'd observe here, this is also called as the Franklin reaction. Now, what has happened over here? Alkyl halide, which is partially charged, comes into contact with zinc, and now with zinc it is most probably a free radical mechanism in the presence of ether which stabilizes these things. What it does is it breaks them into these R radicals which would join together, giving this X radicals coming up together forming X2, which would later on be joined with zinc. So it is most expected way to understand, the most expected way to understand is this R gets generated due to the presence of this zinc in the presence of Rx, and is also known as Franklin reaction. Mechanism for this isn't that important, neither do we need to waste any time over here, but I'll already explain what is it uses, how do we expect it to happen, right? So with that known, you could easily approach and solve problems based on this. Okay, so let us not waste more time. Now the next reaction is also there in NCERT and we'll still look at it even for the preparation of ITJ. It is called as the Corey-House synthesis. Now, it is also an organometallic substance, an organic compound stuck with a metal here. Now, you remember a metal is always electropositive than any non-metal. Okay, almost always. So here, copper is present with this dialkyl group, okay, in the presence of lithium. R2CuLi is lithium dialkyl cuprate. This molecule is actually going to give you a way to prepare unsymmetrical alkanes. I've already told you the reaction where the Woods reaction works, that you wouldn't get this, right? But because the separation would become difficult. But in the presence of this copper lithium organic compound, it is going to be easy. I mean, the mechanism here is lengthy, but that isn't important again. So this lithium would first get separated from copper, forming this LiBr, and then this copper compound would replace its alkyl groups to the halogen containing compound. So in simple terms, wherever you see the alkyl groups, just replace this. So that is the trick that you guys can use over here. Just understand that what is the alkyl group that is given to us with copper lithium compound, and just replace it with the halogens. Yeah, you should check out which places it would get replaced and where you can't replace it. There are places where we shouldn't be using it. So here, for example, in the presence of this bromine, it could simply replace it easily. Now, what is this E2O, that is an ether, does here? Ether stabilizes the compound that gets generated in the process. Okay, we don't use water here because that could react with this lithium and copper containing compound. For that reason, we would have to take a suitable medium. That's why we have taken ether. Sometimes, or not just sometimes, many times, the medium does play an important role in deciding the fate of a reaction. Soon we'll be observing something called as Finkelstein reaction. We'll observe how the medium does play a role in order to make the reaction happen. Now, the second type of reactions, guys, isn't what we'll be focusing well on because we've already done that in the previous class. That is the nucleophilic substitution mechanisms. We've already seen if the nucleophile is weak, it would wait for the leaving group to leave. And what reaction mechanism would it show? Unimolecular. SN1. If the nucleophile is strong, it isn't going to wait for anybody. It is instantly going to make the attack. And what reaction mechanism does it show? Bimolecular. Both the nucleophile and the reagent does play the role there, right? So that is another important thing that you guys need to keep in your mind. I hope that also made the sense and you've understood why and how this has happened. Do let me know if you still have a doubt, although we have it in the previous video where we talked about the nucleophilic substitution mechanism. But you could always ask and let me know. Keep on asking your doubts and letting me know if there is anything that troubles you or anything that you have not understood. Now, as I already told you, there is this substitution reaction that could happen in alkyl groups, but is it also possible in aryl groups? Yeah, it is also possible. Many people think that it would undergo SN1 reactions. I mean, for example, if you'd observe over here, this benzene ring, you'd say that, sir, you have a benzene ring. Once it loses this halogen, it is going to form a stable positive ion, right? And X minus. Many of the people would think that. But in reality, the carbon with which the halogen is attached is sp2 hybridized carbon. And because it is sp2 hybridized carbon, it is an electronegative carbon. Electronegative carbon doesn't have high stability for positive charges. And for that reason, that particular carbon never is going to have a positive charge, or even if it has a positive charge on it, it is not going to be stable. Always remember, a positive charge on benzene ring, positive charge on vinylic positions are very, very unstable. So they are not going to get formed. There's one more problem. Here the bond angle is around 120 degrees, right? When that is an sp2 hybridized carbon. Having a positive charge would again affect the bond angle. So that is another trouble that is going to get generated. So it would never follow SN1 mechanism. That is why the kind of mechanism that these molecules do follow is SN2. It would make an attack over here first, and the leaving group leaves at the same moment with this transition state generated. And this complex or this transition state that gets generated would have a bond being broken. You just observe this bond is going to get broken over here. Okay. So when this electron density is going to be attached, when this is going to make an attack over here, you'd for some time get the negative charge. Okay. Two major possibilities are there over here about which we'll learn, or we have already learned. You have already learned in this electrophilic aromatic substitution reactions, right? Two major types of EAS mechanisms would have been taught to you. So this is going to be used here. First, it would make an attack over here, cause this negative charge to be developed. Okay, and then it would come back, this halogen would leave from here. So nucleophile stays there. Now you could just observe what has happened first in the first step, addition. So this was addition reaction. And then with the electron pair coming back, halogen leaving, what is happening? Elimination, right? So what does this mechanism become? Addition elimination mechanism, right? It is a very simple type of mechanism where initially addition of a nucleophile happens and then removal of the leaving group occurs. Addition elimination mechanism. Now remember, if addition elimination mechanism is there, you might ask, sir, there might be a case where the leaving group leaves first and then the addition occurs. Is that even possible? That could be possible depending upon the scenarios. Like depending upon what groups are attached, you could just see the attack of a leaving group or the group that is coming gets affected. You have a few molecules here. There is this electron withdrawing group present over here. Now, electron withdrawing group withdraws the electron density. Since it has withdrawn the electron density, that molecule would be seeking more electron density, right? So the kind of mechanism that it is going to follow is simply an addition mechanism, an addition elimination mechanism, right? So that type of mechanism does have an importance. I was just making you remember what mechanisms do you follow for this aromatic alkyl halides. There are other mechanisms that we could learn, but you let me know, do you want them or you have already learned them? Yeah, that much is sufficient for now. Let us move to the Schwarz reaction, which is a molecule. I mean, for example, if you have an alkyl halide and you want it to be replaced, that halogen to be replaced with fluorine. You know, fluorine is very reactive. It doesn't stay unreacted. That's why it would always be in the bonded form. So if we want to replace that fluorine with this bromine, it is going to be a little difficult. So in order to make that happen, you need this fluorine attached with something that is very big. And if it is big, breaking the fluorine from that big atom is going to be easy. Just imagine one bond is very this stem from this fluorine, the breaking of them would become comparatively easier. So breaking them would make fluorine available. Now this fluorine can easily react in such a way that it replaces bromine. As I already told you, fluorine is more reactive. That causes this fluorine to replace that bromine. So the key rule that you guys can use is the bigger atom, okay, with which the fluorine is attached, antimony, silver. If the fluorine atom is attached with any of those, it could easily be broken down. Okay, broken down to give this fluorine replaced over. That is the key factor that you guys have to have in your mind. So you just see over here, the Cl groups are replaced with fluorine. And you can see at the bottom, this bromine is replaced with fluorine. This is called as the Schwarz reaction. Okay, so with heavy metals, large metals, it is usually being combined. This reaction. Let us move further and look at further more things. Yeah, do like and subscribe to the channel to stay connected. Let us know about your doubts. We have a Telegram channel already created. Do let us know about your doubts and anything that hinders your pathway, anything that you would need my assistance or our assistance with. Do let us know. Okay, everything you can ask. So let us move and understand this Finkelstein reaction. There's one very, very useful thing in this Finkelstein reaction. Many reactions are there where the reactant and the substrates are the only thing that decides the fate, the outcome. But this is the reaction where the medium has much more importance than other things. I mean, obviously substrate and product are important, but then the medium is the cause for the reaction to shift in the direction where we want it to be shifted. So the medium that you would take over here is acetone. Now, acetone has a capability to selectively stabilize sodium iodide, sodium bromide or sodium chloride. So in the presence of acetone, what happens is, let's say if you have NaBr, okay, and in the presence of acetone, what would happen is this NaBr would react with, let's say, we just say NaI. It reacts with Rx or RBr, RCl or something. Okay, RBr or Cl. Now, in the presence of it, acetone doesn't allow NaI to be stabilized. Okay, it doesn't allow NaI to be stabilized. It just let it be there. It splits Na and I plus. Okay, Na plus and I minus. Now, this I minus says that if it replaces that alkyl group, I mean that R group or Cl group, it ends up forming NaCl or NaBr. And you know, acetone has high affinity towards them. It would attack them, stabilize them, and precipitate. And for that reason, what would be left out is this iodine. So R gets connected with this bulky iodine. It is then very stable bond. But what is it that causes the reaction to shift in the direction that prepare an unstable substance? Is this NaCl, NaBr being more, stable in acetone, right? So that is the cause for the reaction to happen. This is an example where you use the Le Chatelier's principle. How many of you have learned the Le Chatelier's principle? Could anybody let me know in the comment section or in the chat box what is this Le Chatelier's principle? Do let us know. So this is one unusual reaction and a very useful reaction, right? So hope you have understood it. Use this for your knowledge and your answer solving skills. Let us move further, understand more. Now there are cases where KCN or AgCN shows the nucleophilic action. Let us see what happens in that. Let's say if you have KCN, you guys might know KCN splits into K plus Cn minus I. Now in this case, if you see AgCN, okay, AgCN, just observe that KCN is ionic, but AgCN is covalent. Now because AgCN C is bonded, the free atom is is nitrogen. So let's say if you have Rx over here and if you have Rx over here, you could clearly see that here Cn minus makes an attack on R and the end product is simply RCN, where the connecting atom is carbon. But in the second case, carbon isn't free. So the attack happens from nitrogen. And if that happens, we have clearly, we can clearly understand that this N is going to be attached to the alkyl group. And for that reason, RNC would get created. You guys might know this RNC is what we call as alkyl isocyanide, right? And the previous one was a nitrite. Just observe, just because this molecule was covalent, the carbon atom was bonded and wasn't free, right? And so the attack has happened in such a way that it has resulted in the formation of isocyanide. On the other hand, the other molecule was ionic, and that caused this molecule to show or to form a substance that would result in the formation of a nitrate. So just observe the difference and tell me these things differ and what is the major differences that you have observed. Try thinking or pointing out the processes like this that you have come across and do so with them as well. So let us move further towards other mechanisms. Now, as I was already telling you, there were reactions where we had seen the possibilities of other actions apart from nucleophilic action. Let us say we have a nucleophile, but you don't have hello Lekpal, good evening. So we don't let us just imagine that we don't have a compound where you have an acidic where you have a carbon that carries partial positive character. Now if the carbon, yeah, not an issue, you could ask your doubt, but we've just started anyway. Started this course. So what happens in the presence of a base is the base is going to make an attack on proton. You've already been learning the action of a base and how is it different from the action of a nucleophile. Just imagine if you would have had a nucleophile, it would have made an attack over here. But if you have a base, the action is going to be completely different. It attacks the proton, children. It attacks the proton, takes out the proton, and the electron that is there would be shifted to the next bond. If only there is a group that could go away. And if there is nothing that could go away, the basic action isn't going to work out this way, right? So we should understand the difference between the nucleophile and the base. The red ones are going to tell you how the nucleophile works. The blue line shows you how a base works. So we could just understand in cases or in situations, you could very well see the action of a base instead of the action of a nucleophile. And remember, a base would result in the formation of an alkene. Why? We'll see with mechanism. Okay, although I have already shown you a brief overview of how the thing happens in the presence of a base and a nucleophile. We had a session where we talked about the differences between a base and a nucleophile as well. Do let me know if you have a doubt in that as well. So let us move further, understand a little more. How many types of elimination reactions are possible? Basically, two types of elimination reactions are possible. One is the alpha elimination. Two is the beta elimination. Well, what is alpha and what is beta? It's very simple. If this elimination is happening from the same carbon, then it is going to be called as the alpha elimination. For example, if you check out this molecule, this carbon having chlorine, another chlorine, a hydrogen. You could just see that the carbon atom is just one. It is just one carbon atom where both elimination of whatever is there is going to happen. That is going to be called as alpha elimination. If everything that is going to get eliminated is from the same atom, that's alpha elimination. It is very rarely used in our curriculum, so don't worry about it for IIT JEE as well. And Reimer Tiemann reaction and few more reactions only we'd observe. I'll also tell you about that. The other one is beta elimination reaction. That is the one where we would need to focus really well on. With this beta, we'll understand what does this beta mean. Just observe this carbon. If you observe this carbon, this is attached with halogens, okay? This carbon is attached with, let's say, halogen, and there is another carbon next to it which is attached with hydrogens. Now if you call this the atom of interest, okay, or let's say if we call this the atom of interest, okay, this is alpha position, this is beta position. So if the elimination is happening from beta carbon and alpha carbon, we would call it the alpha elimination. We would call it the beta elimination. If it is happening from same carbon, alpha elimination. Okay, the difference is very simple to understand. I'll explain you. But this beta elimination can be of different types. You can have even mechanism, E2 mechanism, and even CB mechanism here as well. What is the E1, E2, even CB? Talk about them in detail. E1 refers to unimolecular mechanism, a mechanism where you just have a single substance involved in the rate determining step. Hello, Harshit. Let us understand. So as I was telling you, in E1, it is a unimolecular reaction, like how we had SN1. The same way E2 is bimolecular reaction. What is unimolecular? What is bimolecular? I don't think there is anybody who has that. Unimolecular refers to a reaction where just a single atom or molecule gets involved in the rate determining step, while a bimolecular reaction is the one where the reaction depends on more than one, actually two molecules in the rate determining step. The third one is even CB, where CB refers to conjugate base. Okay, we'll observe about this property. Let us just go ahead and see them. We'll first understand what is this alpha elimination, although that is not very important, but yeah, it is going to be used a lot in ribothermal reaction and even carbene formation. Now what happens is this OH minus in the presence of a molecule like this, it simply takes this proton by giving its electron to the proton. So it acts as a base by abstracting this proton, causing the electron pair over here to be shifted to the carbon. Since the carbon gets a negative charge, it is unstable. So for that reason, one of the chlorine says, okay, I'm happy to take away your negativity, and takes the electron and runs away. That becomes stable because that wants an electron anyhow. So it has got it. But then what is left behind? No charge, but just the pain, the electron, right? And that molecule is not charged, but it has a pair of electrons. You know what do we call it? You have already seen this is an intermediate of 4 types that we have talked about. It is called as a carbene. With 2 chlorines, it is dichlorocarbene. Okay, so this is one of the methods in which alpha elimination takes place. Why alpha? Both hydrogen and chlorine has been released or eliminated from the same atom. For that reason, it is called as alpha. Observe that both halogen and hydrogen are being released from same atom. Okay, 1, 1. And for that reason, it is alpha elimination. I hope alpha elimination is clear. This much is sufficient for alpha elimination. What is important is this beta elimination. We'll talk and see about beta elimination. This beta elimination, children, happens in the presence of heat when elimination reactions usually get preferred at high temperature due to entropy change, actually due to the positive entropy change in that way. This is going to be preferred at high temperature. More number of product gets created, and that's why it would move towards higher entropy side, where more products gains more entropy or gives more entropy. That depth now isn't important. But remember, this elimination reactions gets favored at high temperature. Okay, now what does happen? We'll look at the beta elimination. In case when you have a group attached to halogen, which is carbon, and having a hydrogen, since the carbon is next to the carbon of interest, if this is the center of interest, this is alpha position, this is beta position. Okay, so in the beta position, you have a hydrogen. In this process, 2 atoms are going to be replaced. One is this halogen, and from the second beta position, there's a hydrogen. These 2 things are going to get released from here. One is this halogen from alpha position, one is the hydrogen from beta position. For that reason, we call it beta elimination. Oh yeah, one more thing here is you'd get other byproducts which has not been listed here, that is H2O, KX. So you can just see, you have 3 different products. And you could understand at high temperature, the entropy increases and the reaction gets favored. The reaction moves in the side where more number of products get generated. Entropy increases. What is the second law? delta S should always be greater than 0. It increases, and for that reason, at higher temperature, this elimination gets favored even over substitution. That's only for advanced, so let us move into the topic particularly. We'll look at E1 mechanism. Hello, Amrit. Hope you're healthy. We'll just understand how the mechanism works. So we'll see here for E1 mechanism, we have to have, a hydrogen we have over here, a halogen. Hello, Lovepreet. So you have this bromine over here and you have this group. Now what happens here is you would see this molecule happening in such a way that it would result in extra stability. For example, in this case, you have a bromine or some group like this. Okay, just imagine if this bromine has to react in the presence of a base. Okay, let's say you have OH minus or you have something that has got a negative charge. But what would happen is, if this is not reactive, if this is less reactive, okay, if this is capable of waiting, like many people would be impatient, they wouldn't wait. Even refers to unimolecular elimination reaction mechanism. Okay, Amarpreet? Lovepreet. So this is, I hope you would have heard me. What I told is even refers to unimolecular elimination reaction. So if the base is less reactive, it would allow the leaving group to leave. Okay, so this leaving group would leave first. And when the leaving group leaves, what would get generated over here? I hope you would have heard me. So you've got this positive charge developed. With that positive charge developed, the molecule has got some stability. Why? Because there is resonance stabilization due to the delocalization of that electron pair. But positive charge is anyway charged, so we don't have that stability, right? And for that reason, this base would now become active. See, okay, yeah, there is this instability created in the compound. So it checks out that there is something that it could work out with to stabilize the compound. And that is, it would stabilize the compound by taking out the proton. And that would result in the formation of another double bond. And this base with hydrogen getting attached. So let's say if B minus was there, it would take up the hydrogen, forming BH. So you could just observe that there has been another double bond created. There's another reaction given above where this Br leaves first, causing this carbocation to develop over here. And after the carbocation development has happened, this H2O or whatever the base is over here. I'm Gyanendra Amrit. So with this base over here would have its action. Okay, this base would attack a proton that could re-stabilize the compound. Remember that a positive charge is still a charge, wouldn't stabilize. Even if it is stable, you don't want it to be anywhere. You'd want it to get neutralized again. Okay? Yes, Samrit, I'm Gyanendra. So this base would take up the hydrogen, and this hydrogen's electron would still be left out there, and that would make up a double bond over here. So I hope you would have got the idea that how does this hydrogen being taken out would result in the formation of a double bond, right? And that is how the thing works out, right? Any doubt here, anybody? Amrit, Lovepreet, or Amrit, I don't know, what is it? Okay. So this is the point that you guys would need to understand, okay? And that is the thing here. All right. My name is Gyanendra Sahu. Okay. So you have this reaction happening in this. This is called as E1 mechanism. Okay. E1 for unimolecular. The next mechanism is, with this one, knowing, we could understand a little bit more. For example, you just understand you have a tertiary alkyl halide, you have secondary, and you have a primary. If anybody would ask you which one would show as E1 reaction faster, it is simple. E1 reaction happens wherever carbocation is stable. If carbocation isn't stable, E1 reaction isn't going to work out that well. Okay, so just observe here. In this case, what happens is this, that this OH minus takes out this hydrogen, and once it takes out this hydrogen, that electron pair that we have over here would have to move over here, right? So before that happening, what would happen? This Br, as I already told you in E1 mechanism, what would happen? First, the leaving group leaves. So when the leaving group leaves, what charge would it leave behind? When this bond breaks, it would leave behind a positive charge. And that positive charge would be neutralized by this hydrogen being taken out and a double bond being generated. So that is the catch, children, that you would need to understand, that E1 reaction gets very dominatingly present if there is a tertiary group that you have. Okay, so it would result in the double bond formation over here, resulting in this wire compound. So I hope you've got the idea that how does it work out. First the leaving group leaves, then the base does its work, takes out a proton, the double bond would get shifted to a place causing, that one bond from hydrogen gets shifted, causing a double bond to be created. Why does that happen? Is to neutralize that positive charge. With that known, I think you have got enough idea about how do we approach this type of things, right? So let us move further towards the next thing here and understand about rearrangement. As I already told you, since a carbocation gets generated, do you think the reaction stops there, holds there, or directly comes to the product formation? No. If the carbocation gets generated, that carbocation, if there is the possibility, would undergo rearrangement. How? Let us. You just observe there's this carbocation over here, right? And this carbocation isn't very stable over there. If the hydrogen from here shifts to this place, the carbocation would get developed over this place. And carbocation over this place would have 3 hydrogens over here, 2 hydrogens over here. Carbocation over this place would be more stable. Why would it be more stable? Could anybody tell me? You guys can let me know in the chat section or anywhere. Okay, so you just observe this. I'll tell you why is this more stable. It's very simple. If you have a carbocation over here, you could observe that there is 3 hydrogen over here, okay, 2 hydrogen over here, and 1 hydrogen over here. The total 3, 4, 6 hyperconjugations are possible. But over here, 3 and 4, just 4 hyperconjugations are possible in the first molecule. None of them that doesn't have resonance. So understand that this one has 6 hyperconjugation, this one has 4 hyperconjugation. And because of that reason, you could clearly see that the second one is going to give you the major products. And so this one here is the major product. Okay, and it's going to be more stable. With this carbocation, you could have got 2 alkenes. One is over here, one is over here. In both the cases, which one is more stable? This one is more stable. One more thing. If you look at over this molecule, you could just count 3 over here, 3 over here, 3 over here, 3 over here. It's 6, 7, 8. Total 8 hyperconjugations of that. So in the second case, whereas this rearrangement has generated this alkene, you can clearly observe that the more stable alkene would be the one that has major, that would get formed in major amount. So we always need to look for more stable alkene. How would you find that out? Using the electron shifting effects that you have already learned. So everything is interrelated in organic chemistry. If you understand one thing well, you could use it in other places to understand or to solve them. So let us move further, understand more things about this. This other thing is this question. Just give it a try. Let me know how would you approach it. All the answers are also given. Just observe that in the presence of water and at higher temperature, even water could act as a base. What water does here is it would cause this hydrogen from this place to be taken out. First, this molecule goes out. Why does it go out? Is because the carbocation could become, when that carbocation generated when it goes out gets stabilized due to resonance from benzene. And after that, the base, even water, could take out this proton, causing the double bond to be generated over there. Okay, so that is the major cause for the reaction to get initiated over here, even with water. So this would take out the hydrogen, make the double bond form, and that would result in the formation of this one. There is one more thing that would get generated over here, that would be because of the double bond formation from the other side. Let's say if this hydrogen gets taken out, then the double bond would get formed over the other side. That's why both possibilities are going to be there. Okay, so that is also needed to be kept in mind while you're thinking about this. Sure. Fine, then let us move to this other thing, this other one. Now, if you'd see here, you have H2SO4. You know, H2SO4 is an acid. So this electron pair of OH would make an attack over hydrogen. When it gives electron pair to hydrogen atom, it forms this. Okay, it forms something like this, and that would make it a very, very good leaving group. Okay, it makes it a positive charge, it makes it a positive charge species. Once this positive charge species gets developed, it goes out very easily. And once it goes out, it again forms what? A carbocation. Okay, and after the formation of carbocation, things are again same. If there is a possibility, it would undergo rearrangement. If there is no possibility, it would not undergo rearrangement. How do you check for possibility? See the stability. So here, if you observe, the alkene that would get generated are of two possibilities, right? You could get it generated over the left, you could get it generated over the right. Okay. If you get it generated over the left, the number of hyperconjugation you would need to check. Wherever it is more, that is where you would make it more stable. Okay. So like that, you would get these two products created. Hope this is clear and you've got the idea of this as well. You know, if you've got any doubt, we'll talk about that and rectify that. And then the next one is E1CB mechanism. It is elimination reaction with conjugate base mechanism. So far we have been seeing that the leaving group leaving first or attacking group attacking, right? But in case of E1CB, things happen little different. In this case, the substrates aren't the same. The substrates do have different behavior. For example, let's say you have a hydrogen, you have a carbon atom, you have another hydrogen. So hydrogen, you have a leaving group attached over here. You have, let's say, CH3, you have NO2 group attached. Okay, you need to have something like this, or you may have to have fluorine or something that stabilizes the negative charge. So in this case, the base would act first. Okay, once the base acts, it takes out the proton. And when it takes out the proton, it forms a negative charge. And why does it form a negative charge? Is because the negative charge that has been formed over here is stabilized by the resonance of NO2 group or any other group that could stabilize the negative charge. And observe that the other thing stays as it is. The leaving group still hasn't left, right? This molecule, because it has lost a proton, this has acted as an acid. What is the other thing act as? The one that has been formed when an acid gets released. It's very simple. If this has acted as an acid after losing a proton, you already know the conjugate system. Conjugate species are those species that differ by 1H plus ion. Since it differs by 1H plus ion, it is a conjugate base. And because it is a conjugate base, the mechanism, since it proceeds with the formation of this, it is conjugate base mechanism. After this, the reaction proceeds in a very, very well manner as SN2, as E2, and this group attacks over here, this group leaves. So the formation of CNO2 as it is, CH3 over here, and the double bond over here, CHH plus leaving group with a negative charge. So this alkene gets generated. Observe that the reaction has proceeded further with the formation of a negative ion. And for that reason only, it is going to be called as a conjugate base. Initially, an acid was there which has lost a proton, forming this conjugate. And that was the reason why you got or call it E1CB, conjugate base mechanism with unimolecular reaction. Okay. So here also the rate determining step would involve only one substance, and that is why it is E1, unimolecular. I hope this also makes sense. Many people would have told you about E1CB and like that they would have just written the normal substances. Remember that a negative charge would get formed if there is something that could stabilize it. Right? So you should check that out as well. So this is the catch, children, that you would need to understand. Okay, remember that. Let's move further and understand few more things about it, about the other mechanisms related to this. There is something called E2 mechanism. When let us not dwell into it, it is simple. That is similar to what we have been seeing. One unusual thing about E2 is it has its own behavior. Like for E2, you have other requirements. We'll not be talking about E2 today. We'll be covering it up in the next session. But before that, you let me know about whatever we have talked about, till whatever topic we have. You let me know about your doubts. Tell me if there is something that is still confusing you. Practice the problem and check out if you could understand, use them for your benefit. This is our Telegram channel link. You could subscribe, or you could get to this channel for more information and asking your doubts. Also, like and subscribe to the channel to get us in touch with you, or to be in touch with us, so that all the things that we do or bring life for you could come to you easily. Whatever work we are doing for you should reach you at least. Okay, then take care, bye bye, and all the best for you.